Okay, thank you, ladies and gentlemen. Good afternoon, and thank you for joining us in this session. And I'm Mantan Albert. I'm going to be the host, and joining me is Professor Catalina Spataru. Professor Spataru is a professor in global energy and resources. She has wide experience with issues related to small island, as she's the founder and director of the Islands Lab at the University College of London. Next, we have Dr. Eileen Zafir-Ratu, who is a business development manager, and she has wide experience in the field of renewable energy, in particular solar energy and wind energy. And we then have Dr. Xiao Xing. She is from Hong University, Shanghai, and she has been working in the field of ocean energy, renewable energy. So before we start, so the session is going to be about innovative solutions for climate resilience and adaptation. Now, I want you to reflect a bit about the term climate resilience. Climate resilience is something that countries have been trying their best to implement over a number of years. And when we talk of small islands, that's where I come from, we're talking here of decades. There has been many measures which have been taken, mitigating measures, adaptation measures, policies, community engagement, okay, and many more. But at this point in time, where do we stand? At this point in time, if we have to rate it on a scale of 1 to 10, unfortunately, we know that we are not far. We have not even reached the halfway through. So there would be challenges. That's the reason why we are here. That's the reason why we are in this situation. There would be some challenges. So one possible challenge could be the uptake of certain measures, mitigating measures, adaptation measures. And with that, I'd like to invite Dr. Eileen to talk a little bit about the different projects that she has been involved, okay? So can we have some more slides, yeah? Okay, so we're here. Dr. Eileen, please.
Thank you, Manta. Thank you so much for the introduction. Go there? Okay. Great. Thank you so much. Yes, thank you all for being here today. I'm excited to present some practical events, some practical facts about natural hazard events and how they have impacted infrastructure, energy infrastructure in particular on islands. We will start with a few examples here, only a few examples from around the world. First is, as you may see, a broken wind turbine on the island of Evia in Greece, where I come from. This was a wind turbine that was not maintained properly, and due to strong winds, it was collapsed. Then we will move into Caribbean islands when in 2017 a hurricane season unfortunately caused massive destructions into onshore PV projects on certain islands where other islands remain intact. And this is an interesting discussion that we could have later, the differences between islands in the same region. Then in Bahamas in 2019, huge floods caused massive power disruptions, and they damaged a significant number of PVs on rooftops. And then at last we have a case in Japan in a PV floating system. Japan is not the typical small island, but still has suffered traumatic, catastrophic events in the past. And here we see the results of a failure in an anchor in relation to strong winds and ciliating movement that destroyed a floating PV on a dam. It is worthy spending a few minutes on a particular case, the Scottish Islands. Scottish Islands are in the periphery of the Scottish mainland, and they have been suffering from continuous climate change impact. A recent event is a year ago when the Shetland Islands remained for almost a week without electricity. In this context, a workshop was held in the region, which revealed significant concerns from the locals regarding particularly these catastrophic events, increased storminess, floods, winds, and their concern not only in terms of direct impact on human life, properties, critical infrastructure, agricultural land, but also it revealed increased levels of stress and anxiety for the islanders because of these events that happen quite frequently. We could stay here and discuss for hours on several different cases that have impacted coastal areas and islands across the world. However, it all comes down to one major question, which is how to develop best practices for designing renewable energy plants, emergency technologies, and restoration strategies to respond to climate change. To answer this question, we need to bring on board different types of actors and stakeholders. The government, local authorities, IPPs, private parties on islands should all come together. One major way to protect our islands is to invest in local infrastructure and resilience. This could happen through submarine interconnections, but also investing in diversification on the island itself. Reinforcing local grids, control centers, distributed power networks could support islands towards any type of natural hazard event. Looking at the project level, there are also some certain advices that we could follow when it comes down to a renewable energy project on an island. For example, we could use PV panels of high loads when it comes to solar projects. For wind farms, it is advised to use wind turbines with larger ones that are more endured to fatigue loads. Never use any self-made constructions, have in place structural engineering studies and a standard process from the beginning till the end. Also, it is important to have local maintenance teams that could respond in sufficient time in order to avoid causing huge profitability losses for the small producers, but also long duration in power interruptions. And having already mentioned about issues at the project level, here we have an example of a wind farm. Wind farms have been the most vulnerable technology so far to climate change impacts. Here we see the lifetime of a wind project, starting from its inception, permitting, construction, and operation. Of course, when it comes to natural hazards, the most sensitive and vulnerable phase is the one during operation of a wind project, which usually lasts 2 to 3 decades. Nevertheless, all the previous stages entail a certain risk which are transferred to the operational phase, because one of the most important factors is the design of the project, the geographic location, where it is, altitude, distance from the coast, and all the different microclimatic conditions which will eventually shape the wind profiles and the climatic condition profiles of this wind farm. It is worthy also making a reference to the main actors that play a role during the operation phase, which is, of course, the project owner. Then it is the operation and maintenance team, which makes sure that the project is operated and maintained properly, and, of course, the insurers. The O&M team usually has limited liability. They're only responsible for the mechanical failures. And when we are talking about any kind of man-made or natural hazard events, the risk is mainly with the project owner, which also tries partially to transfer the risk to the insurers. Nevertheless, as claims regarding natural hazard impacts are increasing constantly, we've seen that insurers are taking a step back meaning that they put in place higher deductibles and they cover limited business interruption loss of income. Here are some statistics collected from a 10-year period regarding the frequency and the severity of insurance claims. What is evident is that windstorms is the #1 reason for insurance claims from wind farm owners. But when it comes to severity, this is shared between flood and wind-driven water and also windstorms. It is particularly interesting to mention that the #1 reason for making claims is reflected through these types of events is lightning. Lightning has been a major headache, I would say, for most of the insurers. And as wind turbines grow, they become taller, have heights, larger blades, lighter blades, while in parallel, the old fleet already installed, particularly in Europe, is aging more and more. The risks are becoming more evident and more prominent, creating, we could say, a vicious circle for loss of profitability, both for wind farm owners, but also for insurance companies. Having already discussed about the islands, what they've been suffering, and also at the project level, it's interesting referring to some microscopic results. These results are from my PhD thesis that was conducted a few years ago. They concern particularly Greece and the Greek islands. Here we modeled a number of scenarios which were assessed against the energy trilemma index. And what we've seen is that for the majority of islands, a combination of submarine interconnections with local utility-scale battery storage, while combining with PV and wind farms, could be or is actually the most favorable solution. There is an exception in general for very small islands which are distant from the continental part. For these type of islands, such as St. Eustatius, which is a very, very small island, it is better and more sustainable for the future to install local smart grids, including from smart meters, battery storage, small hydro pump, solar, and wind. The benefit is not only for the local islands, however. We could see a huge impact at the national level, meaning Greece as a country. Greece could save 22 billion euros over a period of 3 decades from subsidies to oil, because most of the Greek islands until today operate via local diesel generators. And having already discussed about these prominent and flagship submarine interconnections that are already taking place between Greece, the Greek islands, and the Greek mainland, Greece is also leading the way with some key initiatives. One of these was also endorsed here at the COP event a few days ago by our Prime Minister, who came to sign an MOU with Masdar in order to decarbonize a small island, the island of Poros. It's next to Athens, with a main focus on ferries transportation, cold ironing, and lower environmental impact in port infrastructure. It's not only Poros, there are several other islands in Greece that exemplify with some pilot projects. Let's not mention them all right now, but we can discuss later. Greece is also taking some first steps regarding blue economy, hosting for the first time our own conference next year. And at last, I left a very interesting initiative, which is called the Island of Hope. It's from the locals for the locals, taking place on a small island in northern Greece, the island of Samothraki, where a young group, a dynamic group of young and educated people is trying to collect feedback regarding the challenges and the needs of islanders and to pass the message at higher governmental levels in order to improve their daily lives. Thank you.
Okay, thank you very much, Dr. Elin, for sharing the experience on the uptake of different technology and the changing environment, which are enabling a quicker uptake of this technology in small island. Now, there is a second factor that we have to be aware of, and for small island, even the IPCC has highlighted that. Firstly, the extreme events that we are recording nowadays, in the future, in the near future, it's likely to increase maybe twice more, even 3 times more. And when we talk about that, and when we talk about storms, we realize that already storms are becoming stronger and more devastating. What does that imply? Are certain technology adapted to this type of environment? Can certain type of ocean energy technology strive in these types of environment, or is there a need for a new approach to developing or extracting that ocean energy? And with that, I'd like to invite Dr. Jing to talk about the ocean renewable energy. Thank you.
Thank you. Good afternoon. Thank you everyone being here. I'm Jin from Shanghai Jiao Tong University of China. And so I'm going to take some technologies as response to our climate change. And so till now there are 2 main energy recovery strategies for island the energy recovery in the world. The first one just based on the multiple energy requirement based on our island, but this method has their own limitation. And to have limited, one is limited capacity for providing the energy, and the second is it has the weaker resiliency performance for the energy recovery process. And another method is we can take the energy from the mainland and just by taking this and so using the electric passenger ship. And we also can using the submarine cables to transport the energy for energy recovery for the islands after the island discovered. And so, but this method has 3 disadvantages. So just like that, the time consuming and will cost very high investment, and it also has some big risk for the energy recovery process. So in these conditions, we need to develop the safety and high efficient method for the energy recovery for the island. And we also need to use the flow of the renewable energy and to establish our long time without the interruption technologies. And because between the 2 different kind of microgrid the connection, so we need the intelligent fast connect method to make a good connector. And so that is why we developed the hybrid system. And so as we know that the solid oxide fuel cell and the gas turbine hybrid system with a very high power generation efficiency of more than 15%, that is very higher than our traditional ship and our others traditional power generation efficiency. And also has fuel diversity, can use lots of the methane, the biogas, the biogas, and the ammonia, hydrogen, and others liquid fuels. And since these technologies used using our ship power systems, so we can improve the efficiency about the 13%, and also reduce the oil load. And so here, that is the simple schematic of the hybrid system. And so we found that if here we using the liquid fuel, and the fuel will enter the burner, and actually we can use the catalytic burner and to prevent the heat for the reformer. But we can use the reformer technologies to to get the high concentration hydrogen and to drive the solid oxide fuel cell to work. And after the fuel cell work, so we still have a very high temperature energy and a high temperature resource, so we can drive that the gas turbine. And so till now, our ship power generation is based on the gas turbine and also based on the internal combustion engine. And as we know that the internal combustion engine is based on the combustion technologies, has a very low efficiency and heavy pollution performance. And so if we use this technology, we can improve the efficiency and improve the lifetime and also can reduce the emissions. And after that, so we can get the electricity. So we found that is the DC, because in the future the power generation for the ship is all electric propulsion ship systems. And so after the gas turbine, so we can get the alternated current and using AC to DC converted, so we can get the electricity for our users' requirement. And after that, so okay, so because these hybrid systems can use lots of the fuels, especially the renewable and the biodiesel, the biomass, and methanol and ammonia, hydrogen oil, also can use in the liquid natural gas and other hydrocarbon fuels and so on. And here is a typical efficiency diagram compared with others. Okay, so in these figures, that is ours, all the thermal agents efficiency. Okay, so this line is just for our traditional the ship power generation, the gas turbine simple cycle, and this green lines show our internal combustion engine for our ship power generation, and our purple lines just show the solid oxide fuel cell gas turbine hybrid system. So we can find that if we want to establish a big power scale for the ship power system, so this is the power output, and their efficiency will increase with the different power output. And based on this famous advantage, and so we established the hybrid systems floating power ship. So here, this slide just show the schematic of the two different microgrid. Here is the island microgrid, and the left figure that is our floating microgrid. So we, for our design condition, we designed the two floating microgrid, and in our ship floating microgrid, including SOFC GT hybrid system, so we have two sides of the power generation. We also use the solar panels. And so after that, so we develop flexibilities multiple function connector to make there have a good connection to transfer the electricity. Okay. And so after that, because based on above technologies, we use make this Zhaoshu Islands in South China Sea, and so we have several experiment. Here, as for the Zhaoshu Island, there are 100 people live that island. So if we take that technologies for the energy response for the islands, so we need to establish the 1.56 megawatt as OFC, and from the 600 kilowatt from the gas turbine, and also from the 500 kilowatt PV for this island village energy recovery. Okay, so really hope in the future we can use these technologies in our other islands. Okay, that's all.
Thank you.
And thank you.
Thank you. When it comes to the adaptation to climate change impact, what we also know is that we need to move very fast, because climate change is a driver, it's a system which is happening much faster than we are currently able to cope. So with that, I'd like to invite Dr. Catalina Spataru, who is in fact the main important person behind this whole event. And she has lots of experience, so she's going to share with us a new approach or a systems approach that can help us move much faster. Dr. Catalina, thank you.
Thank you, Manta. Right, so what we do at Islands Coastal and Research Laboratory at UCL in London, we explore ideas to support the climate change resilience and adaptation. And here I'm going to show you an example of a 3D model for an island and the combination of technologies, and we visualize first potential of different technologies and combination for islands and innovation, and we look at adaptation and different solutions and find the optimal solution for particular islands. So very much we start from the concept to a printed 3D model to a computer model, and when I'm talking about a computer model, it means this, lots of numbers and big data behind those models where we capture complex system of interactions between resource use, energy, water, land, food, and materials. Here is an example of a blue-green toolbox which helps for decision makers and to channel actions. And what we do here is we develop mathematical models where we look at the trade-offs between resource use, energy, water, food, materials, and land. And then we input all sorts of data around people, energy usage, water, land, food, waste, and climate. We take into account different geographies and biodiversity. And then we can look at the environment, economic, social, and technical aspects of that. And then we do the validation with various stakeholders with our tools. And then we look at the demand, supply of particular islands, and also looking at different innovative solutions. So what we count is we count on different scenarios for different technologies composition, for different climate change scenarios, and very much our purpose is to look at the trade-offs between resource use and cascading effects in systems and services. Why we are doing that? Our primary aim is to respond to 5 humanitarian questions, and one is what is the extent of hazard when we have an hazard. So in this case, for example, we looked at floods, how many people are affected, how the exposed population is being affected, how the infrastructure has been affected, what are the resources and sectors at risk. So that is a really important step where we use our complex models and big data and artificial intelligence behind that. And then we looked at the pathways for systematic transformation, and then we discuss that with different stakeholders, and then for them to take the decisions. What is the big vision here? The big vision here is we will have all sorts of different floating systems. So it could be this floating, for example, we convert the ships, as Jing mentioned. We can effectively have floating power systems, and I will give you some examples in a minute. And then we connect all of them into an interconnected system, and wherever we have a deficit, for example, or a surplus in some parts of the world, then we can bring that and utilize it. And that is not only about climate resilience and adaptation, but also is about net zero, no? Because we are going to go for more electrified system, we are going to have more electrical vehicles in the system and so on. So all of this needs additional power, and that could be additional power which comes from these floating systems. Right, so what I'm going now to do, to take you a little bit through a bit of a exhibition, a virtual one, of course, and that is coming from my passion for art. And I will take you a little bit on a walk for these future solutions for climate adaptation, which we are researching in this moment. And here are some 4 types of systems which we are experimenting and doing a bit of research. So these are different floating power systems based on wind and solar, ocean and wave energy, wave, wind, and solar, and then the last one on a chamber which pushes the waves through a narrow channel and then spin a turbine connected to an island. So each of these capture different energy. So for example, if we look at the second one, is a floating power system which capture the up and down motion of waves and convert it into electricity using hydraulic piston and the generator. And the method is also known as point absorber. And it considers a buoyant that floats on the surface of the water and mounting system that anchors it to be seated and then is connected to can be connected to an island. The advantage of the system is very simple, adaptable and scalable. So we can have this in many places in the world. The third one is a power system which combines wave, wind, and solar energy to produce electricity using turbines and PV. This method is also known as a hybrid. We call it hybrid renewable energy system or multi-source platform. What effectively we have here is a floating platform that supports different types of energy converters, like wave energy converters, wind turbines, solar panels, and then we connect that to the shore by a cable, and then we carry the electricity generated by the converters. So this method also has some advantages, being able to harness multiple sources of energy and also to reduce the variability of intermittency of each of these solutions. The fourth one, it's a bit more complicated, uses a wave capture chamber that pushes the wave through a narrow channel and spins a turbine. What it does is really consisting of a partially submerged structure that encloses a column of air above a column of water. And the waves, what it does, it enters and exits the chamber through an opening at the bottom, and this causes the water level and the air pressure inside the chamber to oscillate. And then the electricity produced by the generator is then transmitted to the shore via an underwater cable. So I did a little bit of analysis in terms of cost and financial cost. And here are some estimated costs, because of course when we talk about cost, this involves many different parameters. So for the type 1, where we use an absorber and heaving buoyant to capture up and down motion of wave, then we have an estimated cost, levelized cost I'm talking here, of about 181 euros per megawatt hour for a total of 100 megawatt installed. So you can see the difference between the different systems. There are different costs which, as I said, depending on the material of a system, depending on many other, so this is an approximate cost for the levelized cost. So then the question here is about how we learn from nature as well, because we can have all sorts of different systems, and but it's important to embrace nature as well and becoming friendly with the nature. So here are some other visions of future systems which we try through research and simulation to see which one could work. The first one shows how wetlands can be integrated with floating microgrids by using plants that can grow on floating platforms such as water hyacinth or water lettuce or duckweed, and these plants can also produce biomass that can be used as a source of energy or fertilizer. And this is what you effectively see in the first example. And why is this purpose? The purpose of the system is to support the wetland system and the wave energy converter, and the platform is effectively connected to the island by a cable that carries the electricity generated by the wave energy converter. The second one is an algae integrated with microgrids by using photobioreactors, which are devices that can cultivate algae in controlled conditions such as temperature, lights, nutrition. And the photobioreactors bioreactors can be installed on floating platforms or underwater and can be powered by renewable energy sources, solar, wind, or wave. And the platform then is connected to the island by a cable that carries the electricity generated by the solar panel. The photobioreactor produces algae that can be used as biofuels or bioplastic, food or feed or even pharmaceutical purpose. The benefit of this system is also that the photobioreactor also can sequester carbon and release oxygen. So there are many benefits of this type of a system. And the third one show how artificial reef can be integrated with floating microgrids by using materials that are compatible with marine life, such as concrete, for example, but we need to be sure that we use it in a sustainable way. And then these artificial reefs can also be designed to incorporate renewable energy, such as wave, tide, or ocean thermal energy conversion. And this can support the wave energy converter and the tide turbine. And then we can connect it again to an island by a cable and then to convert that into the energy we need. In terms of estimated cost, and also impact to environmental zone. We did some research on that one. So estimated costs could range from $1,000 per kilowatt for the wave energy converter, in addition to about 10 per meter square for floating platform, and wetlands plants also is an additional cost for that one. In terms of operational cost is for the wetlands and wave is about 0.05 dollars per kilowatt hour, and that is less than the algae and solar and then artificial reefs, waves, and tide. As you see, this is really approximately because depending on the location and depending on the materials you use for the systems and many other factors there. Then in terms of, we did some estimation of environmental score, carbon emissions also on carbon content, so you can see the difference between the three systems. But of course, more research is needed in this area to see which one could work or not. So very much the kind of a vision we do in terms of combining research with design is about, the biggest vision here is about how we can interconnect all these systems and help us to reach this net zero, as we discuss all the time about the net zero, but also how we bring climate resilience and adaptation into it. And then this can happen only if we have different stakeholders, and there is where you see in that diagram there the blue economic sectors and the green economic sectors. So we need all these stakeholders around the table to support us doing more research in this area, but also to take decision in terms of a policy, in terms of regulations, because it's an area where it's very much a gray area in this moment, and we need to have more answers and more support.
Thank you very much. Okay. So can we have time for a few questions? Yes, one question over there.
I've got the okay without a microphone.
Yeah.
Thank you. So I wanted to ask Catalina, did you look at the way in which the growth of coral can be used to underpin the structure in place of concrete?
No, we haven't looked at that. Definitely is not our area because our area of research is more on the energy side, but we are collaborating now with others working on that area and trying to understand what is. But it's absolutely an important area to understand, especially if you are talking about coral reef, what we are doing with that and to get it right.
Did you look at the positives of the artificial coral reef from the point of view of coastal protection?
No, we haven't looked. No, it's, yeah. Absolutely. Yeah. Okay. There are other teams, research teams working on that area for sure, yeah. Collaboration is key, to be honest, in this area too, because it's a massive topic. You can see from the perspective, but what we look at for technical and financial calculation and modeling.
Hi, I'm Dr. Claire Nelson. First of all, I'm just so excited to see 4 women up there talking about engineering work. I'm going to be running or supporting the Center for the Blue Economy in the Caribbean region. And all of what you have all said is very important to what we're doing. I also have a project I'm doing with the University of Mauritius in the space agenda. I'm just wondering how how might we create like a collaboratory around how we share information. Because one of my concerns is that people are doing all this fantastic work. We come to a conference, we hear this information, and I have tried unsuccessfully so far to get the Alliance of Small Island States to create sort of a technical working group, not just a political working group, but a technical working group around energy, water, wastewater management, and waste management, the four, I think, critical issues. So have you given any thought to that, or can we probably have a confab after this session to really think about what next? It's all well we can hear everything, we're excited, and we each individually reach out, but how do we really take this and work with universities such as the ones that I am attached to in the Caribbean and in the US to create something that we can really begin to test these models. I'd love to test a combination of this in the region of what you're doing. And the second specific question is about tidal. Is there any of you working on tidal energy? And lastly, we're doing some research on water-powered, converting diesel engines to water power.
Yeah.
And I'd like to share that with you and see if we can do something with that.
Okay, thank you very much for your question. Absolutely. So I embrace your frustration in terms of not communicating enough or not having there a platform, an international platform where we can share this research. For that reason, I see Innovation Islands is a perfect platform of bringing us together. Now, for that reason, we are here in this room, and for that reason of many other activities and so on. Unfortunately, as researchers and as an academic, you don't really have a time of setting up any kind of platforms or organizing and so on. So this really needs to be on itself and then bringing us into it, into the conversation. So I don't really have an answer, truly, but I do really understand what you are saying. We are having exactly the same frustration. For example, in my laboratory, we have been doing case studies, more than 400 case studies across the globe, and then everyone is like, oh, okay, guys, you're doing really extremely great work and so on, but then many times it's about funding. And there is where, for example, the four of us are together here is because I have a project where Manda is part of it, University of Mauritius is part of that one. We work also University of Ghana with Japan University and so on. I have another project which I'm collaborating with Jing with SGTU, and then of course Eleni was part of my team. So you see, you bring this kind of research or partners together in time through research projects. This is what we do. You use research projects, sometimes consultancy, sometimes philanthropic grants, but it depending really on the chance, to be honest. So, but I would really encourage, if any philanthropic organizations or individuals wishes to invest in this, this is the momentum, to be honest, because we can't wait for climate change, you know, as we see it, or all sorts of events we see there happening, you know, and we have a research, but we need more research, and we need more investment into research. In terms of the tide, and yes, we do research. We look at the ocean, wave, tide, solar, wind, and so on, so I can talk after that about this.
Maybe I'd like to add very quickly that the Indian Ocean Commission and the International Labour Office are actually collaborating to set up a campus des métiers de la mer. That's going to be for job creation, and networking would be part of it. So we will be able to share that with you later on. So I think we have two more questions.
Yeah, thank you. So Simon Dant from the Sustainable Ocean Fund. Just really a follow-on question, I guess, to the previous one is, I mean, why is it that islands are still so using heavy fuel oil or diesel as a source of generation? Why are we not making the change? Is there, I just don't quite understand why we're not making more progress.
Maybe this one, I'll take it. Coming from an island, I would say that lots of effort are being put into renewable energy. Lots of possibilities are being considered, even biogas, wind energy, PV, and also the discussion around ocean renewable. But the problem is that, first of all, there is issue of land space for biofuel. There is issue about technology, let's say, the grid, the electricity grid sometimes cannot absorb all the renewable from PV. There's also the need for locals to be incapacitated in terms of knowledge on how to go about relying more on solar energy. And there are many new initiatives, like more recently, just a few days ago, people were talking about combining PV, like a PV farm, whereby there's going to be agriculture. So the initiatives are there, and of course, being a small island, funding is a main challenge for us. Okay. So next one. Yeah.
I'm sorry, but
yes, I will conclude.
I'm short for time,
So,
so please feel free to talk.
So thank you very much. Please join me to thank all the panelists, and also a big clap for you also for your participation. Thank you.